Hello, welcome to Berkshire Guitar Amplifier Repairs. Stuart Smith with you as always, and today we're going to be looking at how to read schematics for guitar amplifiers. Now let me tell you straight away, if you can read schematics even halfway decently, you probably don't need this video, because I'm going to aim it at pretty much absolute beginners. This was requested by a viewer, and in particular he wanted me to look at the Fender Concert amplifier. There's no particular amplifier I need to do specially, so I may as well do that one for him. And we're going to be walking through the schematic step by step, and hopefully at the end of it you'll have a bit of a clearer idea of how to read them. Of course, you know, there's no substitute for several years under your belt, but you've got to start somewhere, so let's start now. It's going to be a bit of a chalk and talk, I'm afraid. There's no real getting away from it. So only watch if you really want to understand guitar amplifier schematics pretty much from the basics upwards. Okay, here we are, and a good place to start is with the block diagram, so that when we get on to the main diagram it's not so opaque to you. So here's the block diagram of a pretty standard valve guitar amplifier. This little symbol here usually means an input jack, and this little symbol here means ground. So we have our outer ring of the input jack is grounded, and the inner ring is taken to this first section here. This is the pre-amplifier. This is usually your 12AX7s, ECC83s, 2, 3 or 4 of them in the amp, and all that this is doing is boosting up this very low signal. It's only a few tens of millivolts here, tens of thousandths of volts, boosting it up to, I don't know, 5 or 10 volts peak to peak here. So loads of gain going on here. And this can be as fancy as you want. It can be a simple preamplifier, or it can have overdrive sections, and even some effects can come off here. There might be some links here to a reverb spring or something like that, or a tremolo, but let's not worry about that for the moment. Let's keep it simple. So here's your 12AX7s, ECC83s. The signal then gets passed through to the power amplifier. So this is the heavy lifting. These are your power valves, your 2 EL84s, your 4 6L6s, your 4 EL84s, or whatever it is you've got in the amp, doing the heavy lifting. And it takes this input signal here, amplifies it a little bit, but in particular provides output current to drive the output transformer. So that's a bit of ironmongery you've got in your amp that makes it quite heavy. And that matches the output of the power amp to the loudspeaker, and in particular, by the way, isolates it electrically so that you can't get any high voltages, DC voltages on the speaker, because of course these are touchable terminals. I've only showed one, but this is a block diagram. Of course there are 2 connections coming out to the speaker and 2 connections coming in here. So standard block diagram. Here's your speaker or speakers, and that's it, job done. Now all of this lot needs various voltages. So for example, the heaters on your valves, the little torch bulb thing that glows inside them, that needs 6.3 volts AC to drive them. Sometimes there's a valve rectifier instead of a diode rectifier. I'll be talking about that in a moment. And strangely enough, the valve rectifier needs 5 volts for its heaters, not 6.3. So sometimes you'll find, as well as the 6.3 volt output, you've got a 5 volt output. And then of course you need HT, which is the high voltage, and that could be several hundred volts, 300, 350, 400 volts DC. That needs to be provided to the power amp, and a couple of hundred volts to the preamp valves. And then of course you have bias. I won't go into too much about bias in this video, but basically that's a negative voltage, so that we can set our power valves at a tick over rate, a tick over current called the bias current, and that's a negative voltage. So already we've talked about 4 different voltages we require. 6.3 volts for the heaters, 5 volts for the heaters in some amps, several hundred volts for the HT, and also the negative 50 volts usually for the bias. That's all provided by the power supply. Another big chunk of ironmongery in your amp, great big power transformer normally, and a load of smoothing capacitors, the great big HT capacitors that smooth the output from the power supply. So going into the power supply we have live and neutral, and earth just goes to ground like that. First thing the live and neutral does is go usually into a big transformer, out the transformer into some sort of rectifier which takes the AC and changes it into DC, bit of a lumpy DC, and then the lumpy DC is smoothed out by the HT caps which give it a nice smooth DC. Of course when I'm talking DC I'm talking now just the 300 or 400 volts for the HT. And the minus 50 volts has a bit of smoothing too for the bias. The 6.3 volts and the 5 volts, if it's present, are all AC voltages. It's only a torch bulb effectively, so it doesn't really matter which way the current goes through the filament of that heater in the valves. So I hope that's clear. Now that'll make a bit more sense now when we come onto the actual schematic. We can start linking this in with a genuine schematic. So let's have a look at the schematic for the Fender Concert. Here we go. Schematic for the Fender Concert, model AB763, or that's the schematic for it. Fairly typical valve amp, and I think if you saw that without having seen this you'd be thinking what the, and it's all quite complicated, isn't it? And it takes a little while to learn your way around it. Anyway, let's just go through it. I'm not going to go through every single item on this, but I just want to give you a good feel and get you started. I'm aiming this at absolute beginners. So if you remember, we had a guitar amplifier input and a pre-amplifier stage, which I said was ECC83s, 12AX7s and that kind of thing. So here we go, look. The input jacks aren't quite shown as I showed them. There are different ways of showing it, but anyway, here's one input jack here on the vibrato channel. Here's a second input jack, and down here on the ordinary channel, one input jack, another input jack. Now, I don't know how much knowledge to assume that you have, but why don't I just very quickly say that these squiggly little things here are resistors. These parallel line things here are capacitors. These are valves. All these are valves there. Diode. What else haven't we seen? Transformer. There's the one there, and there's one here, look. This is supposed to be the windings on the transformer, with some iron laminations and some more windings on the secondary. That's how that's supposed to be depicted. Anything with an arrow through it like that is you can't see it terribly clearly on this diagram, is a variable resistor. In other words, a pot. There's one there, look. And fun enough, they've done it differently here. They've got the arrow going into the middle of the resistor. Again, that's a potentiometer wiping up and down to pick off different resistor values. Every circuit diagram has its own quirks, and sometimes they show things a little bit differently to others. But let's just work with this one. So let's start off. We can start off anyway. We can start off with the power supply, but let's pitch right in with a normal channel and see how that fits in with our little block diagram here. So what we're looking for is a guitar input and some stages of amplification, pre-amplification there. So let's see if we've got that. Okay, here we go, coming in on these jacks here, and look, it goes into half of an ECC83. That's what that semicircle means, because an ECC83 or 7025 or 12AX7, they're all pretty much the same. Preamp valve has two valves in one. So this is one valve. That half and that half is all in one. This is not an ECC83, but they're all in one envelope. So it's got two valves in one. So here's the first half. That allows you, by the way, to have two gain stages in one package. Otherwise you'd have dozens of valves and things. So so it comes in here, look, into the grid of this preamplifier valve. I'm not going to go into how a valve works. I have made videos on that. There's the anode, there's the grid, there's the cathode. So varying a voltage on that grid briefly allows you to vary the current up and down between the anode and the cathode. And that's how you get amplification. So it goes into one stage of amplification. It comes out here, look, and goes into a bit of bass, treble and tone control. That's marked treble, that's marked bass. and then it comes off of there, look, it comes into another section of amplification via a volume control. That little arrow there means ground, so that's the equivalent of my old-fashioned ground there. I think you can see that if we wound this pot down to ground, no signal would get through. So you turn the amplifier right the way down. If you wound it up to here, you're picking up maximum signal. So that's how your volume control works. So we've amplified one stage, typical gain 100 or something like that. Another stage, we're going to lose some through this tone control. You always do lose some signal through there. So the signal's weaker here than it is coming out of here, so we need to amplify it again. So another gain of about 100 there. Out we come again, look. Coupled via this capacitor, I might come back and do a bit more detail on here, but coupled via that capacitor and this 220k resistor, where does that go? Ooh, it goes into what's looking like our power amp section here. Now before I get onto that, let's just go to the vibrato channel, and it's virtually identical, look. In fact, I think it pretty much is identical to this. So we've got two identical channels of amplification here, but the vibrato channel is modulated by this little bit of circuit here. I won't go into this too much, but it's basically another ECC83 configured as an oscillator. So basically it oscillates like that, and that has the equivalent, that has the effect of kind of putting a volume control here, where you go like that to modify the volume. And that's what gives you your whoa 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 vibrato effect coming there. So you don't get any vibrato on this channel, you do on this channel. Again, I may come back and have a little bit of a look at that, but you can tell immediately, look, the vibrato pedal comes in here and turns this oscillator off or on. There's the speed control, look. So that tells you how fast the oscillator is oscillating. So whoa 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 whoa, like that sort of thing. And this is the intensity, how much of this signal we allow to modulate the main guitar signal. When it's down to ground, look, there's our ground again. When this is wound down to ground, there's no intensity, and all this signal gets through to the power amp. You don't hear any vibrato. When you turn this up, it allows this to modulate that signal and give us the vibrato effect. Notice that these two signals are just mixed together here. 220k resistor there, 220k resistor there. So whichever you plug into ends up at this point here. Right. Now, what happens after that? Well, this is a very typical setup here, in that we have another ECC81 in this particular case. 12AT7 is an ECC81, very similar to the ECC83. I won't go into the differences. And this is configured as what's called a phase splitter. You've probably heard the term. This is your V3 normally. You know, the valve just before the power valve is usually what's called a phase splitter valve. And you normally buy one that's balanced, and that means that both of these halves produce the same gain. Remember I told you that there are two valves in each envelope. Well, you want both of them to be similar gain, otherwise you'll end up with a bigger signal here than you do here, and that will drive these power valves unequally, and you'll end up with, wait for it, a little bit of distortion on the signal. Oh no! Please, no distortion on my guitar amp. So what this does, this phase splitter, is it takes this single signal in. Look, remember this is our signal here, comes in. I won't go into the details of it. It's actually quite complicated how this works. And what it does is to produce two anti-phase signals here and here. So in other words, when this one goes up, this one goes down. So they're out of phase with each other. Same signal, but going opposite phase to each other. And that's, as you know, is called push-pull. And this signal here drives one power valve, this signal here drives another power valve, such that when one valve is pushing, the other one's pulling, when the other one's pulling, the other one's pushing. So we get this push-pull effect here, dum, 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 and that drives current through this output transformer primary one way, then the other way. And of course, you know, if you drive current through a transformer one way, then the other, then one way, then the other, you know, that's just AC. And if you stick a secondary winding on it there, you can pick up that AC and use it to drive a speaker. And that's exactly what happens there. So phase splitter takes a single signal in. Don't forget, here we've got this, just a straightforward signal. Splits it into two. Sorry about a different frequency there. That looks like twice the frequency of that. Splits into two anti-phase signals to drive the power valves in a push-pull arrangement. Now here are our power valves. Here, in this case, two 6L6s. And here's the ground point look. So the cathodes are grounded. The plates are held at a high voltage via the center tap of this transformer, which, let's just follow that down. This comes down to the HT output, the 440 volts HT DC output, 440 volts there. We'll do the power supply in a moment. Consider that to be 440 volts DC. Look, it goes to the center tap of a winding of a transformer. Transformer's got no resistance, so it's pretty much 440 volts there, 440 volts there. When I say no resistance, I mean low. It'd be a few ohms if you measured it with a meter. So you can pretty much say the 440 volts is there and there. In other words, on the plates, look, in fact they've marked it, plus 440, plus 440. And then, so when this valve is on, it draws current down to here. The current goes through here, this half of the valve, round there and down to ground, look. So remember, it's going that way. Now when this valve, then that valve goes off here, this valve comes on, and now the current comes through here, down there, through there and to ground. And that's how we get that alternating effect there. You might wonder why we do this complicated push-pull. I won't go into it. It's a fairly efficient way of gaining power. The other way of doing it is Class A, where you just have a single valve and a speaker pretty much in the anode. But we won't go into the difference between Class A and Class AB. Suffice it to say, it's a very good system for amplification. Its only downside is it has a little bit of distortion on it, because when these valves change over from pushing to pulling, can be a little tiny issue round about the 0 volts level, and so for hi-fi amps, people don't like this push-pull arrangement because they want their 0.00001% distortion or whatever. But for guitar amps, it's absolutely perfect. So here we are. Look, secondary of the output transformer looks going to ground. Look, one side's grounded, and then that just drives our speakers. Notice the advantage. Look, we've got 440 volts on one side, DC, on one side of this output transformer. That will kill you stone dead if you touch that. You certainly don't want to be having touchable speaker terminals anywhere near 440. So this isolates any DC. It's impossible, unless the transformer fails, for DC to get through to here. Strictly AC. So that's another reason for using an output transformer. Okay. I hope you're happy with that. If we had a 100 watt amp, we would just see two 6L6s here and two 6L6s here, just doubling up on the valves to get double the power. Otherwise it would be completely identical to this. Now let's have a look at the DC power, let's have a look at the power supply side of things. Don't forget, we have to produce all these voltages that we need. Well, first of all, let's trace from the beginning. Here's our power inlet cord here. And that's an AC outlet. Ground switch. This is an old amp. We wouldn't have that these days. Here's the off-on switch. Look, which breaks the live coming in. Let's call this live, and let's call that neutral. So turning that off, of course, would break the current. Here's our fuse. Look, which if that blew, it would completely stop any current going through here, and so it would kill the amp. So don't forget AC again, so it's 240 volts AC going through the primary of this transformer like this, backwards and forwards, backwards and forwards. One cycle of current's going that way, the other cycle of current's going that way, backwards and forwards. Through the transformer, it's picked up by the secondaries here, and the turns ratio here tells you what output voltage we'll get. So if you had like 240 volts in and you want 6.3 volts out, which we do here, look, here's our 6 volt winding. Well, I don't know, you got 40 to 1 turns ratio or something. So for every 40 turns on the primary, there'd be 1 turn on the secondary here to get that voltage. But similarly, look, we want 320 volts AC or 640, you know, across the winding there, and so you need to step up. So for every, you know, 1 turn on here, we might need, you know, 2 turns here or something on the HT winding. I mentioned earlier that some amps have valve rectification and require 5 volts. This amp does not require 5 volts as it has diode rectification. If it did have 5 volts, you'll see another winding here which said 5 volts, and that would do the heater for the rectifier valve. So we are now on the DC side. Here's the 6.3 volt heaters, does all the heaters for all the valves, and also does the pilot light, little torch bulb basically. Here's our diode rectification. So diodes pass current only one way, and this rectifies the AC, which looks like this, into DC, which looks a bit sort of like this. Still sort of AC-ish, isn't it? But this portion of the wave is flipped up into there by the rectification process. Then we're going to smooth this. So instead of that, we get like this on the first stage of smoothing, and then on a bit more smoothing we get hardly anything, and then the final smoothing we get a nice DC 400 and whatever it is they're asking for, 40 volts. How do we get the smoothing? Via these HT capacitors. Here is the first stage of smoothing, and they've put two 350 volt 70 microfarad capacitors in series with each other. And if you put capacitors in series, you get half the capacitance. So in other words, this capacitor here looks like a 35 microfarad capacitor at 700 volts, because you double the voltage. Why have they done that? Because back in the day, a 70 microfarad 500 volt capacitor either didn't exist or would have cost a fortune, but 350 volt capacitors were, you know, common. So they put two in series and save themselves some money and get the voltage that they need on there. This 350 volts is the working voltage of that capacitor, DC. Any more than that, you risk the capacitor shorting out inside. Just for your interest, these two resistors here literally divide whatever voltage that is, there's ground again by the way, look, in half. So this is half V, where that is V. And it just makes sure that equal voltages across these capacitors, because if you don't have those, you can end up with 400 volts across one capacitor and 200 over another or something, you know. So they do this to balance up the voltages on the capacitor, make sure they both get the same half voltage. So there's our first smoothing of HT. Maybe it looks something a bit like that, and it's kind of 440 volts ish. You know, might have 10 volts of ripple on it, so it might go 430, 420, 430, 420, whatever. Here's our standby switch, look. So with that open, no HT gets to the valves, so they cannot conduct and they cannot produce any sound. No current will go through them. Close the standby switch and you immediately apply this 440 volts to the next stage of smoothing. Here's a choke here, it's a little transformer, and that acts as a bit of a smoothing too. Now notice that this 440 goes straight to the center tap here. So it's obviously smooth enough for their purposes via this effectively 35 microfarad at 700 volts capacitor they've dabbed across there. Now we produce some other lower DC voltages here via this chain here. So look, we've got another smoothing capacitor, an HT cap of 20 microfarads, then a resistor, then another capacitor of 20 microfarads, and a resistor, and another capacitor of 20 microfarads. And this resistor capacitor combination does a lot more smoothing and makes you a very nice DC. albeit at a lower voltage, 375 volts, look, compared with our 440 volts. We haven't lost a lot, 65 volts or something. Why do you want to do all this smoothing? If this is good enough for here, why can't we just send it off there? Well, the answer is that the preamplifier side is more susceptible to hum, which of course is what this is. This is hum, mains hum. It's more susceptible to that because you're doing a lot of amplifications. You have a little tiny bit of hum on here, and by the time you've amplified it up 100 times, amplified up another 100 times, you can get quite a reasonable hum here. So you want this to be as hum-free as possible, which is why they put these shields on the first valve in an amp, and sometimes they don't bother with the successive valves. You want to stop the hum in the very early stages of the amp. So anyway, we end up with 375 volts here, which is about right for our pre-amplifier HTs. They don't really want 400 volts on when they want less than, usually 200 or 300 volts. And as you can see here, by the time we've gone through this resistor to the anode and this resistor to the anode here, we've got 275 volts, which is about right for a preamplifier valve. Very common to have 100k in the anode of the amplifier. I personally find it a little bit difficult. I've always used to having high voltage up here and like 100k. If I want that to go to 100k, I would normally put 100k up to my 375 volts there, rather than, so it's just convention. But it seems odd to have these resistors going down, but that's how it is. So basically 375 coming in through 100k through this valve and then down through this resistor here to ground. So that's how that works. Same with the vibrato channel, a normal channel look, sorry. We've got our, where are we? 375, where's the DC here? Here, oh, they've just marked it as D, which is D. That's D there, there's D there, look. So rather than taking this line down here, they've just put a D there. Same deal here, look, 100k, 100k. In you go. Okay, that's now the basic walkthrough. You've pretty much got it. Preamplification, power amp, phase splitter, power amp, output transformer, and then some DC and various voltages generated by the power supply section. Let's go into it a little bit more depth though, because if you remember, we have to bias the power valves, and that just means setting the tick over current. We're not talking AC now, we're talking about the tick over current of these valves. We need to set that at 30 or 40 milliamps or something like that, and that's done by putting a negative voltage, DC voltage now on this grid here, negative DC voltage. The more negative you make that, the less the electrons that want to rush from there to there. Negative electrons want to rush from the cathode to the anode. It sees a lovely tempting positive 440 volts. It wants to rush across there. If I make that negative, they'll get repelled back down. And if I can tune the negativity there, only some get through, and that sum is our bias current that we want. So we tune these two grids here at a certain negative voltage, typically minus 35, minus 40 volts or something, to turn down the flow of electrons here so that we get our tick over current of 35 milliamps or whatever. So you see this is marked minus 48 volts here. So down we come. Let's follow this down. Oh, we've got a little bias pot there. Bias pot on an amp, oh, that's rare. This allows us to, there's ground, look. So the more we go that way, the more positive we go, funnily enough, because ground is more positive, isn't it, than minus 48 volts. And the more that way we go, the more we pick up this voltage here, which is probably minus 55 or something. So this allows us to pick up a voltage that suits us well, and they've asked for minus 48 there. That a lot depends on the actual valve you put in there. Stick a bias meter in, turn the pot, get the current at 35 milliamps. How do we get our minus 55 volts or whatever it is there? Well, we come off this tapping here. It says 50 volts AC. So we've got 50 volts AC tapped off here, through a diode rectifier, through a smoothing capacitor, in this case 25 microfarads at 50 volts, to produce a negative voltage there, not a positive one. Let's say minus 50 volts. I don't know exactly what it is. And that's taken off this pot here, and does our bias here. So that's how we get the bias voltage, the negative bias voltage. Feel free to stop anytime you're watching this if you've had enough. I'm just going to go into it in a little bit more detail, as much detail as you want. Really, I could talk for 10 hours on this, I guess. But let's just look at something else. Let's have a look at this little vibrato circuit here, which is quite interesting, I think. First of all, notice it also picks off a minus 50 volts here. Don't worry yourself about why, but that allows this oscillator to function a little bit better. So I won't go into great detail. To be absolutely honest with you, I don't know in great detail how this oscillator oscillates. I know in vague detail, but I don't know exact detail of why they want minus 50 volts on there. So basically what we have here is an oscillator. It's achieved by these three capacitors here, which you can often see in an amp. They're like, you know, three big disc capacitors like this, all together in the amp. In fact, I think I've got an amp actually open. Let me just see if I can find that for you. Yes, by an amazing coincidence, I've got a, not exactly a Fender Concert, but similar kind of amp open on the bench at the moment. I'll show you in a moment, but let's look through the rest of this and I can show you all the components on that amp. So these three capacitors, they do phase shifting if you're interested. You know, if you can take the output of something, invert it, and feed it back to the beginning, it'll oscillate. And these three capacitors produce enough phase shift of the signal to allow that to happen. This oscillates, and this buffers it. So out of here, you're getting quite a slow sine wave. You're getting a sort of whoa, 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 quite a slow sine wave coming out. And the way they achieve the vibrato is they have a little roach, as it's called, a little photocell and a neon light all wrapped up in some black plastic. And this light flashes, it's a neon light, a little neon, and it flashes at the speed of this oscillator. So basically it goes flash, 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 flash. If you turn up the speed, it'll go flash, 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 flash. Turn it down, it goes flash, 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 flash. And because this is all enclosed in the dark, it's a photocell. In other words, the more light you put on it, the lower the resistance of this resistor here. When the light's on, this is low resistance. When the light's off, this is high resistance. Now that looks quite interesting, doesn't it? Because, again, it's weird having that ground symbol pointing upwards. So that's a ground symbol there. I would have had that coming out here through there and to ground here. But anyway, there you go, that's ground. So if that's a low resistance to ground, in other words, the light's on, look. Here's our main signal, here's our guitar signal here, and we're kind of short, with intensity at maximum, look, up here, we're kind of shorting that signal to ground. So the volume goes down dramatically. Now when the light goes off, this goes high resistance, and so this is still going to ground, but via a big resistor, so the volume comes back up again. So with this flashing off and on, we're kind of shorting this signal to ground, dump, 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 and that's what gives a whoa, 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 whoa in volume. That's how it does, how it happens. Yeah, quite a neat little system, really, isn't it? Let me show you that on a real amplifier. Well, here we go. No expense spared on my demonstrations here. Pure coincidence I happen to have this one open. And let's look at that vibrato circuit. Someone's been in here and changed a capacitor, probably to increase or decrease the speed of the vibrato, the minimum speed or the maximum speed. Anyway, here are the three capacitors I mentioned, the phase shifting capacitors. Only one of which seems to be the original disc. Normally it's a disc like that, a disc like that, and a disc here. So there's the three phase shifting capacitors. Here, look, is the photocell roach, as it's called. Look, just because it looks like a, you know, cockroach or something. These two wires here are the neon. So inside there is a neon, and hard up against it is a photocell, and there's the two connectors for the photocell there. Again, no expense spared for your benefit. Here's one I opened up some time ago. There's the photocell. These photocells go, by the way, they go weak, so you need to replace them. So there's the two leads for the photocell look. And then in there is this neon light which goes up against there. And I think the leads come out the other way, doesn't really matter. And then this is all wrapped up in black plastic to keep the light out from it. So simple little device. The neon flashes, flash, 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 flash. Photocell goes high, low, high, low, high, low resistance, and that effectively acts as a kind of a volume control for it. Whilst we're here, let me quickly show you. This is the little circuit for producing the negative bias. It's exactly like we looked on this amp here. We've got a tap off of the transformer, minus 50 volts, whatever, goes through a resistor, through a single diode, smoothed by this capacitor, then off it goes to do the bias. And we've done absolutely everything on this amp now apart from the screen resistors on the power valves. I won't go into why we have screen resistors. There's just another electrode on a power valve called the screen. There it is there. So anode, screen, grid and cathode. The heaters aren't shown. The heaters are in there as well. By convention you don't show the heaters, it's just assumed that this goes off and does all the heaters. And we need to put a fairly high DC voltage on the grid as well via these grid resistors. And grid resistors can go quite often on amps, so it's always worth checking if you have a faulty amp. And so look, they pick off the screen voltage from this side of the choke. I have no idea why they pick it off from there and not from there, but anyway, someone might enlighten me. So there's our screen voltage there and our two screen resistors. I think we've covered absolutely everything on that. I can't think of anything we haven't looked at. Bias circuit, AC in, DC and 6.3 volts. How we do the smoothing, more smoothing to produce the DC voltages, the preamp side. We haven't gone into detail about what all these components do, but of course that would be a very long lecture to talk you through. But in many ways you don't kind of really need to know, in the sense that, you know, if you start to recognise this is a tone control circuit and a first stage of preamplification, second stage of preamplification, you can start to do quite a lot really. So there you go. I think we'll leave it at that. There's nothing else on that schematic I can see which is important that we've missed. Well, there you go. Hope you enjoyed that. Bit of a romp through. I hope you learned something from it. Don't forget, doing this is all about just experience and having a go, learning a bit more each time. I learn pretty much from every single amp I have in. There's the odd one, I think, oh, I've seen this 10 times before, I know what to do. But I would say 90% of the jobs I do, I learn something from it. And I've been at this 50 years, would you believe? So don't feel bad if you don't understand everything I said there. If you picked up some things, that's great. That's another step on your journey. And next time you watch a video like this from me or somebody else, you'll know that little bit more. And you know, hopefully you'll be repairing your own amps or maybe other people's amps into the future. That would be great. We amp technicians are a kind of a dying breed in some ways, particularly the valve people. Anyway, thanks as always for watching. I'll catch you on the next video.